Hello everyone, welcome to this live stream today. What we're going to be covering is Dynamic NAT. So we're going to be doing a Dynamic NAT Lab. This should be good everyone to see how Dynamic NAT is configured. It's something very important to know for us using the exam. Obviously we've got Dynamic NAT, we've got Static NAT, we've got Portable NAT. So also known as NAT overload. But in this video, we're going to be looking at Dynamic NAT and how we configure it. So this should be a good opportunity for everyone to get to know more about Dynamic NAT. So let's start off. So we're on Boson NetSIM's software. So the objective is well, let me just read the full thing. Dynamic NAT is commonly used to translate a range of private IP addresses on a local area network line into one or more globally unique IP addresses on the internet, which is a global WAN. In this lab, you will configure Dynamic NAT to enable a specific range of hosts on a private line to communicate with an internet host that's configured with a public IP address. So an enabled secret password is configured on the ISP router, which is here, to prevent you from access and on switches. Whilst we've got an enabled secret password on both to prevent you from accessing them in this scenario. So configure the appropriate settings on router A. The enabled secret password on router A in this lab is configured as Cisco. Okay, so we need to configure the appropriate settings on router A. We're going to configure Dynamic NAT to enable a specified range of hosts on a private LAN to communicate with an internet host that's configured with a public IP address. Okay, so we can see a web server here that's configured. So let's get straight into the lab. So in this current topology and consider the configuration changes that will be required to achieve the scenario requirements. So you have been tasked with configuring the network to provide a range of hosts, including PC2, but not PC3. So we need to configure the network to provide a range of hosts, including PC1 and PC2, but not PC3, with access to internet hosts. So the enabled secret password on router A in this lab is configured as Cisco. So task 1 is your organization has been allocated with the 192.0.2.8/29 address range to facilitate internet access for hosts. How many host IP addresses are contained within this range? So the 192.0.2.8/29 address range to facilitate. So it's to facilitate internet access for hosts. So how many host IP addresses will be in that? So if we think back to subnetting, what we have is if we've got a /29 range, if we've got a /29 as prefix, well, that means 29 network bits are set to 1 and 3 network bits are set to 0. So if you multiply 3, so if you look at so we focus on those 3 host bits, we do 3, 3 times 3 times, we do, if we do 3, we take 2 to the power 3, so 2 times 2 times 2, okay, that's 8, okay, and so that's 8 addresses there, but we've got to remember that 2 are reserved, so 1 is for the broadcast, 1 is the subnet ID, so we're left with 6 IP addresses. Okay, so when you've got a /29, a /30, you'll only have 4 addresses coming out of that, and only 2 that are actually going to be usable. That's why we use it for point-to-point links. So if we look at this answer here, we can see that your organization has been allocated with the 192.0.2.8/29 address range to facilitate internet access for hosts. Now, the 192.0.2.8/29 network has 6 usable host addresses. Okay, as I've just said, we've got 6 usable host addresses. Let's move on to the next question. The range of hosts on the private network, we've got quite a bit to get through. Okay, we've got task 1, task 2, and task 3. So this is the planning. Then we implement that now, and then we verify now. So number 2, the range of hosts on the private network that should be permitted to act net hosts must include the IP addresses of PC1 and PC2. However, the range of hosts must also be as small as possible. or subnet of the 192.168.100.0/24 network should you use to achieve this task? How many IP addresses will this subnet provide? The range of hosts on the private network that should be permitted to access internet hosts must include IP addresses of PC1 and PC2. Okay, they both should be permitted. However, the range of hosts must also be as small as possible. 192.168.100.0/24 network should you use to achieve this task? How many IP addresses will this subnet provide? The range of hosts needs to be as small as possible. Now the /24 network, 192.168.100.0/24 network, should you use to achieve this task? How many IP addresses will this subnet provide? So in case you wonder, 192.168.100.0/24. So we've got our router A is using that on its gig, is connected to that subnet on the gig 0/1 interface. Okay, but we need to think about we need to think we need to think about what subnet what we need to think about the subnet that we should use to achieve this task of that network, of that /24 network, 192.168.100.0/24. So let's have a think. Okay, the range of hosts on the private network that should be permitted to access internet hosts must include the IP addresses of PC1 and PC2. Have the range must also be as small as possible. The 9 IP addresses in the range of addresses that include PC1 and PC2. Therefore, any subnet that includes both PC1 and PC2 must have at least 16 IP addresses. Right? The 9 IP addresses in the range of addresses that include PC1 and PC2. If you look at PC1 and PC2.36.46, any subnet that includes both PC1 and PC2 must have at least 16 addresses. Based on the 2n-2 formula, you can calculate a subnet with 4 host bits if 16 IP addresses are required. 2 times 2 times 2 times 2 is 16. So based on the 2n-2 formula, you can calculate a subnet with 4 host bits. If 16 bits are required, 4 host bits means that 4 of the bits in the net 32-bit mask are set to 0 and the remaining 28 bits are set to 1. So 4 in the host portion, 28 in the network portion. 192.168.100.32/28 subnet is the only subnet of the 192.168.100.0/24 network that defines 16 IP addresses and includes the IP addresses of both PC1 and PC2. Okay, so the 192.168.100.32/28 subnet is the only subnet of the 192.168.100.0/24 network that defines 16 IPs and includes the IPs of both PC1 and PC2. Okay, so that is be using. Okay, if I reveal answer, we need to be using the 192.168.0/100.0/24 network. Now, Cisco devices support 3 basic types of network address translation. Why is Dynamic NAT the most appropriate form of NAT in this scenario? 3 basic types, like I said: static NAT, Dynamic NAT, portable NAT. Okay, PAT. NAT overload is also called. There's 3 types. In this case, what we're trying to achieve is we want PC1 and PC2 to have internet access. We want PC3 not to have internet access. And so that's what we're trying to achieve from these 2 hosts to be able to reach out to the internet, this one not to. So there needs to be some NAT going on for that to be it, because these will of course have private IPs, as we can see here, and they need a public IP to get out. Now, in this case, Dynamic NAT is the most appropriate type to use in this scenario, because it provides that dynamic one-to-one address mappings between inside and outside addresses for a range of hosts, and because there's no requirement here that our host must be able to initiate connections to inside hosts. That the hosts on the internet side are able to initiate connections to the inside host. There's nothing been said about these guys having any internet host like the web server here to be able to access the inside host. So static NAT, while that is appropriate for if you have a small number of one-to-one address mappings, in case where outside hosts must be able to initiate connections to inside hosts, because static NAT, right, that requires manual mappings. It does not scale well in scenarios where a large number of address mappings are required. And NAT overloading, special variation of dynamic NAT, and is a solution that is appropriate for scenarios that require a large number of many to one address mappings. Okay, and in this case, we don't need many to one address mappings here. What we need is that the internet host must be able to we need these guys to be able to have that dynamic to one address mapping. Okay, because we just need our dynamic one-to-one address mappings between the inside and the outside. Okay, inside and outside address for our range of hosts, and we've got no requirement here that these guys need to access these guys. Okay, there's no connection initiation required from the web server point of view that's been specified. So in this case, it's fine. We're just doing one-to-one dynamic mappings here, dynamic one-to-one address mappings. We're not doing a one-to-many mapping situation. So if that was the answer to the third question. Let me just reveal one by one. Now, if you look at the fourth question, when the pool of public addresses available for NAT is smaller than the number of permitted IP addresses, when the pool of public addresses for NAT, pool of public addresses available for NAT, smaller than the number of permitted IP addresses, what will happen? Private IP address requires NAT, but there are no public in the NAT pool. So when the pool of public addresses available for NAT is smaller than the private IP addresses, what happens if a permitted private IP address in the NAT pool? Something to think about. So the answer is that dynamic NAT uses one-to-one mappings between a permitted range of private IP addresses and a pool of public IP addresses. When the pool of public addresses available for NAT is smaller than the number of permitted private IP addresses, packets requiring translation will be dropped if there are no available public IP addresses. Okay, so if there are no public available IP addresses in the NAT pool. So dynamic NAT uses one-to-one mappings between a permitted range of private IP addresses and a pool of public IP addresses. When the pool of public IP addresses is smaller than the number of permitted IP addresses, requiring translation will be dropped if there are no available public IP addresses in the NAT pool. Right? So we got that. So when the pool of public IP addresses available for NAT is smaller than the number of permitted private IP addresses, package requiring translation will be dropped if there are no public available public IPs in the NAT pool available. So a root keeps track of NAT address entries in the NAT table. Static entries are permanent, whereas timeout after a period of time. If all of the IP addresses in a NAT pool are allocated, no new entries into the NAT table until one or more of the times out or is manually cleared by an administrator. The default timeout for dynamic entries is 24 hours. However, you can use the NAT IP NAT translation timeout command to configure this value. So that's that 24 hours. However, you can use the IP NAT to configure this value. IP NAT translation timeouts down. So the default timeout for dynamic NAT entries is 24 hours. You can use the IP NAT translation timeout command to configure this value. That's the answer there, that will be dropped. Okay, it'll be, if you've got that, if there are no if there's a shortage of public IP addresses in the NAT pool, then unfortunately those packets that need translation just going to be dropped, because they just can't handle it, you know. So the fifth question is: do all assigned IP addresses on the accessible devices in the topology match their respective values shown in IP addresses table? Do all assigned IP addresses on the accessible devices in the topology match their respective values shown in the IP address table? So we can see here all the IP addresses I'm supposed to have. So if we can verify them, if let's first go into the PCs and we can just verify the PCs. So if I just do ipconfig PC1 192.168.100.38, I know that's correct. I've got another screen open with the lab document, so I know that is correct. Let me show you 100.38. If we look at PC2 now, same thing, ipconfig, we can see 100.46 is what it's supposed to have. That is correct. Let's go into PC3, ipconfig again, 100.54. That's also correct. Let's go into the web server. 100.10. That's also correct. That's the lab document, by the way, with all those IP addresses. So those are all fine. RouterA. Now we're not using the machine, we're on iOS now. So enable password is Cisco conft. Oh, actually, we don't need to even do it to conft. Show IP interface brief. So for interface 0/0 and 0/1, in 0/0 should be 203.113.1, which is correct here, and then for 0/1 it should be 192.168.100.1. So that's fine. Okay, that's fine. Let's go into ISP router now. ISP. We don't need to check the switch. It's not listed in the table. Cisco. Oh, that's not worked out for some reason. ISP router. Maybe that's okay. So the enable secret password on RouterA in this lab is configured as Cisco. I don't know what ISP is. Maybe I don't need to check that. Yeah, that's fine. We don't need to check ISP. I don't think we're supposed to access that actually. So that's fine. We can see the IP addresses of. We check the hosts and the server. So examine the IP addresses table. Which devices in the network topology have been assigned private IP addresses? Examine the IP addresses table. Which devices in the network have been assigned public addresses? So we can see the hosts how will have private IPs. Yeah, we can see that the routers they have. Well, that's a public IP. That's a public IP. Right there. So we can see that the hosts all indeed have private IP addresses. Okay, the switch A is powered on, but that does not have an IP configured. It's just a layer 2 device. Okay, and we can also do the gigabit Ethernet 0/1 interface or router A, gig Ethernet 0/1. That also has a. Don't need to worry about the ISP route here, which that has a private IP 192.168.100.1 as within the private IP space. Yeah. So the next part of this lab is now we need to from you can see so public IP gigabit Ethernet 0/0 interface on router A. All interfaces on the ISP router and the web server are configured with public IP address. So web server. Apologies, that's not a private IP. That's a public IP. That's my mistake. That 192.198.51.100.10. That's a public IP. Sorry, I very briefly skimmed over that. That's 198. If it was 192.168, that would be a 198.51. That's definitely a public IP address. So I apologize. That is my apologies. From RouterA, this is part 8 now. Yeah, task 1.8. From RouterA, attempt to ping the web server 198.51.100.10. Does the ping succeed? Why or why not? So from RouterA, we're going to ping this web server. Okay, 198.51.110, if I remember that correctly. 51.100.10. We can see, yes, the ping does work. The ping works. Now, and then from PC1, we need to attempt to ping the web server and see if the ping works. 198.51.100.10. So that, okay. So that has timed out. Unfortunately, that's timed out. Why has the ping not worked? That's the question. This is the kind of things we need to think about when it comes to TCNA. Why is it not working? Why can't PC1 ping out to that web server? Why can he not? So the reason why is because PC1's configured with a private IP. Web server has a public. There's nothing NAT configured here. There's nothing here to translate the addresses to public IP addresses. That's the purpose of NAT, of course. So what we need to do now is move on to the last question. Let me quickly reveal these. So yeah, that ping worked successful because RouterA's got a public IP configured with ISP as its gateway, explicit route, but it can access the forward the traffic to the ISP router. Okay, and that's connected to the web server. He'll have a route, and the ISP router definitely has route in his routing table for it. Now, this is not being worked out because there's no mechanism, there's nothing, no NAT configured for translation. And one's got a public IP, the PC, and the server's got a private, so it's not going to work right out straight off the bat. So that's question of task 1 is, would you expect to be able to ping either router A or PC1 from the web server? Why or why not? 192.1 or PC1 192.168.100.38. Would you be able to expect to ping either of them from the web server? So router A, that's his public, that's his private. That's his private IP there. That's the private IP there. Would we expect you to ping them? The answer is that you should be able to ping router A, but not PC1. Okay, because a successful ping implies that the source of the IP ISMP echo request has a route to the destination IP address, and the source received an ICP reply from the destination. Okay, so a successful ping, because we already ping implies that the source of the ICP echo request has a route to the destination IP address, and the source received an ICP echo reply from the destination. In this case, we had a ping between router A and the web server. So in this case, as being A is a path to web server, you can be sure that the web server has a path to router A. However, because the PC1 has a private IP address, you can be sure that the web server does not have a path to reach PC1. Therefore, its ICMP echo reply will be unable to reach. Its ICMP echo reply will be unable to reach one. Ping's already worked for A, and that didn't just go to the web server. We had an ICP echo reply that came back. So the ICP echo request is one part of it, the reply is the other part of it, and that's both have worked. The next part of this task is to implement NAT. So we need to make the necessary configuration changes router A to implement dynamic NAT and to achieve the scenario requirements. So 1, the organization allocated the 192.0.2.8/29 address range to facilitate internet access for hosts. Now you must create a NAT pool that includes the IP addresses within the allocated range. Should this NAT pool include only the host addresses with allocated range? Why or why not? Okay, I'm going to try and hurry along this lab now, because it's, we are now 23 minutes into this lab. My aim is to get this lab done within 45 minutes, and then there will be another lab coming out as well later on. That's going to be live streamed. So your organization will be allocated the 192.0.2.8/29 address range to facilitate internet access for hosts. The organization will be allocated the 192.0.2.8/29 address range to facilitate internet access for hosts. You must create a NAT pool that includes in this allocated range. Should this NAT pool include only the host addresses within the allocated range? Why not? Why not? Okay. 2.0.2.8/29 address range to facilitate internet access for hosts. When creating NAT pool, you should include only the host addresses from this allocated range. Only from that allocated range. We should only include host range. It's likely that the allocated range of public IPs will be included in the ISP's routers routing advertisements, and that other devices will consider the first and last addresses and broadcast addresses respectively for the allocated subnet. It's generally considered best practice to avoid using network and broadcast IPs when allocating addresses to devices. Right? So, and as a very, very, so that's test. That's for test 2 part 1. So we should only include the host addresses from this allocated range. Yeah, so we're creating that pool. We should only include the host addresses from this allocated range. It's likely that the allocated range of public IPs will be included in the IP's routing advertisement, and other devices will consider the first and last addresses of that range the network and broadcast addresses. That's like a convention within the network community to do that. Now, on RouterA, create a NAT pool named NAT pool. Okay, nice and easy to remember. NAT pool that includes the appropriate IP address range. Right, so we need to create a NAT pool named NAT pool and that include on RouterA that includes the appropriate IP address range. So how do we do that? Well, let's go on to RouterA. Let's get logged back into there. Privilege X mode. Now we need to what we need to do is to go into global configuration mode. Now this network has 6 usable host addresses: 192.0.2.9 up to 192.0.2.14. Okay, so we need to issue a command to create the NAT pool, called NAT pool, and include the appropriate address range, which is that range there from 192.0.2.9 to 2.14. And that's what we need to do here. We need to create that NAT pool. If we want our PC1 to be able to access that web server, connect to that web server, it needs to be able to, we need to address translation. So let's go into, we're in global configuration mode, IP NAT pool 192.0.2.9 192.0.2.14 net mask 255.255.255.248. Okay, that's that subnet mask there. Apologies, this lab software does this where it doesn't show the full string of commands that I put in, but that's what we need to do. I do apologize that it doesn't show the full. Doesn't show everything I typed in one go. But IP NAT pool 192.0.2.9 192.0.2.14. We configure the net mask there. So we use that net mask keyword there, 255.255.255.248. Remember, 248 two 248. So what we're using. So the syntax of the IP NAT pool command is IP NAT pool. I'm just reading off the document here, but IP NAT pool, insert the pool name, start address, end address, net mask, subnet mask. The start address and the end address are used to specify the first and last IP addresses in the contiguous range of IP addresses that will be available in NAT in NAT pool. Now the net mask subnet mask parameter is used only as a sanity check value to ensure that the start address and end address reside within the specified subnet. Okay, making sure that this in the correct subnet. Now task to let's move on to task 2.3. The private LAN in the scenario uses the 192.168.0 sorry 192.1 private LAN in the scenario uses the 192.168.100.0 address range. However, the scenario requires that only a subset of the host, not subnet, subset of the host within that network NAT. Okay, so the private LAN in the scenario uses the 192.168.100.0/24 address range. How the scenario requires that only a subset of the host within that network should be permitted to use NAT. So can an entry with can an ACL with a single entry be used to define the host from 192.168.100.0 sorry .100/24 network that should be permitted to use NAT in this scenario? Why or why not? So question is, can an ACL with a single entry be used to define the host from the 192.100/24 network that should be permitted to use NAT in this scenario? Subset of the host within the network should be permitted to use NAT. Should be used to define the host from the 192.168.0 network that should be permitted to use NAT in this scenario. Right, so remember we've worked here. This is the public, yeah, range 192.0.2.8/29. That's for, and that was on the internet side. Now we're trying to configure the side. Okay, important not to get confused between 192.0.2.8. That's different to this, which is a private range. Can ACL with a single entry be used to define the host from the 192.168.0 sorry .100/24 network that should be permitted to use NAT in this scenario? Why not? So the private LAN in this scenario is using that range. Can we use a single entry? Single entry. We think about single ACL entry. What do? We specify the access list. If it's an extended access list, what we do, access list. We specify the number of the access list that we want to configure, the access list number. We specify protocol, ICMP, traffic, UDP, TCP, just particular traffic that we want to deny, permit. Then we use the permit or deny word. Okay, so IP. So so permit or deny. We permit or deny the traffic, and we specify source and destination address. In this case, do we just need a subset of those hosts to be able to access the network. So to define the host from the 192.168.100/24 network, should be permitted. Hope you had to think about this. Let's look at the answer. So the answer for 2.3 is that the 192.168.100.32/28 subnet is the smallest subnet of the 100.0/24 network. That includes that includes the IP addresses of both PC1 and PC2. So because PC1 and PC2 can be included in a single subnet, you can use a standard ACL with a single statement to define the host from the 192.168/24 network that is permitted to use NAT in this scenario. Right, so we can use a standard ACL with a single statement to define the host from the subnet that should be permitted to use NAT in the scenario. So now any statement is not required in this ACL because its inclusion at the end of ACL is implied by default. Remember, we have implicit deny. So in addition, Cisco advises against using any statement in such an ACL because it can lead to excessive CPU utilization. It's also something important to remember. So that single entry can be used to define hosts from the 192.168.100/24 network. Permitted to use NAT in the scenario. So number 4, on RouterA, create a standard ACL1 to define the host from the 192.168.100/24 network that should be permitted to use NAT in the scenario. We need to create standard ACL1 to define the hosts from the 192.168.100/24 network that should be permitted to use NAT in the scenario. So let's go to RouterA. Okay, and let's configure an access list. Yeah, so we need to configure an access list to define from the 192.168.100/24 network that should be permitted to use NAT in this scenario. So let's configure that ACK list. We need to give the access number 1 permit. Okay, it's 192.168.100.32. Right, so 100.32. And then 0.0.0.15 is the wildcard mask that we need to use. Because an ACL is used to specify IP addresses and not for IP address allocation, the entire subnet range is considered by the ACL, not just the host addresses. Therefore, every IP address in that subnet, yeah, the 100.32/28, remember we spoke about earlier. Remember these, so sorry about that. My lab is just, there we go. So back in now. So these hosts, remember, when we looked at the IPs, they were within that subnet .38, .46, .54. And if you look at the subnet, if you look inside of a /28 subnet, with a /28 subnet, you have 16 IPs in each subnet, 14 which are usable. Now, that would include that whole range there. Okay, from .30. Okay, so the whole range itself is from .32 to 47. It's from .32 to 47. Okay, every IP address in the 100.32/28 subnet, which the range of IP addresses 192.168.100.32 through 192.168.100.47 will be permitted to use NAT if this subnet is specified in a permit statement. You will need to convert the network mask associated with 192.168.100.28 subnet into a wildcard mask. Now the subnet mask for that is 252.255 dot 1111000 in binary, which would be 240 in dotted decimal notation. And if you subtract 240 from 255, you get 15. That's why the wildcard mask is 000.15. Okay, that's why, as it says here. So we configure that, and that is the access list there to allow IPs from that subnet. So look, we were able to do that. Not even have to use an extended access list. We could just use a standard access list to do that. Okay, if we were filtering like traffic like HTTP or UDP or ICMP traffic, then we'd have to use an extended ACL because standard ACLs can't filter based on those parameters. Now on RouterA, you should issue some commands to configure. Let's go on to the next question. Issue the commands to configure the appropriate inside interface for NAT. What is a NAT inside interface? So we need to issue the commands to configure the appropriate inside NAT inside interface for NAT. Go back to RouterA, and we need to do IP NAT inside. Okay, we need to configure the Gigabit Ethernet 0/1 interface. So remember, when we look at this is the inside address, right? So we need to configure inside and outside. IP NAT inside, IP NAT outside. So what we do is go into the interface. So we can just specify G0/1. And now IP NAT inside. Let's specify that IP. Let's just specify IP NAT inside. Okay. Now, and that inside interface is the interface that's connected to the private network, or the interface that is connected to the network that should be translated. In this case, is interface Gigabit Ethernet 0/1. That would be the outside interface. And the next question is to issue the commands to configure the appropriate interface for NAT. What is a NAT outside interface? So we can see here, this is what we need to do for this part. Now let's do the NAT outside interface. So let's go back to the router. Exit interface G0/0 this time. IP NAT outside. If I can spell it right today, outside. No, that is outside configure. Now we need to issue the commands. So VLANs for that. That's the outside interface. Okay, that connects to the interface that's using the public IP. Yeah, connect to the public network. Now issue the IP NAT inside the source list command with appropriate parameters to allow the host ID ACL1 to access internet host use the NAT pool IP address pool. So on RouterA, issue the IP NAT inside source list. IP NAT inside source list command with appropriate parameters to allow the host identified ACL1 to access internet host networks. So we need to issue the IP NAT inside source list command with the appropriate parameters to allow the host that identified in ACL1. Okay, to the host that in ACL1. Yeah, we need to issue this command. Yeah, with the appropriate parameters that allow the host identified in ACL1 to access the internet host and use the NAT pool IP address pool. Right, IP NAT inside source list. So what do we need to do? So go back into command IF mode, interface configuration mode. We need to do IP NAT source list inside source list. IP NAT inside source list. Specify our ACL. Okay, because remember, we're only allowing the host that was specified in that ACL that we configured to go out to the network. So IP NAT inside the source list 1. Yeah, and then specify the pool. IP NAT inside source list 1 pool NAT pool. So let's look at the syntax. The IP NAT is saying, let's start the process configuring that. Inside source means specify that the source IP address of traffic received on the inside interface should be address translated when it passes out through the outside interface. Specify that the source IP address of traffic received on the source IP address of traffic that's received on the inside interface should be address translated when it passes through the outside interface. Specify that the source IP address of traffic received on the inside interface should be address translated when it passes through the outside interface list. And then we insert that access list number. We're specifying that access list now that we created. That must be matched before translation can occur. This determines that which hosts on the private LAN, on the private network, can and will have the addresses translated and which won't. Okay, so we're filtering which ones can access the network, the public network. Okay, so we're giving it something to check, like just check only these guys, only these hosts, that if they're in that list, that okay, if that matches, okay, then we can do translation for them. Then do translation only. Pool, we just specify the pool name. Okay, that's just a range of public addresses okay, that are going to be used by those private LANs that are in that list. Only if they're in that list that they will be allowed to access one of them from the pool, okay? Remember we specified that here. So if we just now click enter, that's configured there now. Now, well, let's do the verification. This is the part that I think it's this is the fun bit where we have to see the result of what we've done. So on RouterA, issue the commands to display the NAT table. Are there any translation entries currently in the table? Why or why not? So, does anyone know what what command we use to display the NAT table? What we use is show IP. Let's get to the bottom. We have to do show IP NAT translations. Should run this from previous exec mode. So we need to do show IP NAT translations, and we can see here that there are no entries in the NAT table. And why is that? Were you expecting to see something? Well, the reason is router has been configured upon dynamic NAT. So entries are created in the table as permitted. And so entries are created in the table as permitted hosts send traffic from the inside network to the outside network. Okay, so we've configured dynamic NAT. Entries are created in the table once those permitted hosts send traffic from the inside network to the outside network. So let's try and do a ping now. So the next question is in task 3.2 is to do a ping. So for ping 1, reading down, so that from ping 1, attempt to ping the web server 198.51.100.10. Does the ping seed why or why not 198.51.100.10? Ping 198.51.100.10. Yeah, we are pinging the web server now. Remember, we tried to do the start, we could not do it. Let's do it now. Does it work? It does. It does indeed. Perfect. Now let's try it from PC2 and PC3. So let's try do it again. Now ping 192. Sorry, ping 198.51. 198.51.100.10. Ping that web server. Okay, and we can see indeed that we have a successful reply. Now, what about let's ping from PC3? Will that work? What do you think? Will that work? Based on what we did, we based on the access list that we configured, based on the NAT pool that we created, you know, based on that, if you look at this IP address here, that's got an IP address of 54. Now, will that work? Will that work? Based on the NAT pool that we created, where we specified a specific subnet to. So we go back to RouterA. Let's have a look at that NAT pool. Sorry, just closed the terminal down. Remember, we created we created a NAT pool for those that's the public addresses to use, but we also specified an access list. You look at that access list, that's for this subnet. That subnet has 16 IP addresses inside of it. Yeah, that's only going to go starts at 32. That's going to end at 48. This host here has address ending .54. Ending .54, right? The ending .54 that sits outside of that that range. If it's .54, so what's going to happen? What do you think is going to happen? You think that's going to be able to do it? Let's try. Okay, that timed out. That's not worked. That's not worked. And hopefully from my hint that you came to that conclusion as well. It wasn't going to work. Okay. that wasn't. Let's have just reveal the answers now. So firstly, okay, we can see, obviously there were no entries in that table at that time. We did a ping from PC1, yay, it worked, happy days. PC2, happy days. PC3, not good. But that's what's expected. It didn't work. I say not good. It's not what we configured, so it is actually good. PC3 cannot ping the web server because it does not have an IP address selected by ACL1. Therefore, NAT is not performed for its packets, and a mapping is not configured between its private IP address and public IP address from the NAT pool. It's not possible for hosts on the private LAN to communicate with an internet host without NAT. Yeah, so this IP addresses are not in the ACL1. Now, on RouterA, issue the commands to display the NAT table. Are there any new translations currently entered? Are there any new translation entries currently in the table? Go back to RouterA. Let's do show now IP translations again. Do we see any new entries? At the moment, don't see any entries. There should be entries. So this might be a little problem with Boson NetSIM software here, because should be having entries on RouterA now. So let me log out the router completely. Just want to completely get out of the terminal. Enable. Let's do some more pings. Log back in to that router. Let's do another few pings here. Do another ping test. Do another ping test. Do another ping. Let's do show IP NAT translations now. Sorry, it's right at the bottom. Okay, so we can see now translations. Sorry, the software, as much as I like it, sometimes it's it can be a bit glitchy and buggy, but it is, because I think it is a good product despite its issues it can have. So IP NAT translation, so we can see ICMP 192.0.2.9 2144 inside global, inside local, outside global. So inside local 100.38, outside local 198.51.100.10, 2144, 198.51.100.10. Okay, so you can see .2.9 there. Those inside global addresses, outside local, outside global, inside local 192.168.2. So 192.0.2.9, 192.0.2.10, 192.168.100.38, and 192.168.100.4. Dot 192.168.100.46. Going back to PC1, you can see, we just remind ourselves what the IP address was of this PC. This guy here is .38. So that entry here is referring to, sorry about this, .38. That is PC1 there, and that will be PC2. That's the inside addresses. Those are the inside global addresses for them that correspond. Remember, we configured a NAT pool range for them to use from, and it looks like they are using from that, which is good. 192.0.2.9 and 192.0.2.14. So sorry about this, guys. This lab has run over time. 198.51.100.10 outside global addresses there. So there should be command. So if we just have a look at the final answer for this lab now, this lab completed. On rotate, you should issue the following commands to display the current state of the NAT table. There should be now entries in the NAT table indicating that ICMP sessions exist for both PC1 and PC2. Indeed, there is. Output of this command times out quickly. So if you do not see both entries, you can issue the ping commands quickly on PC1 and PC2 and reissue the command. So this does time out quickly. It told us how long or this may not be here next time you run this. So you see, it does actually time out quite quickly. And perhaps that was the issue. That was the issue the first time around the pings, that they just timed out. That's why it didn't show, rather than being an issue with this actual software. That might have been the actual case. So that is the lab done now. So I hope you learned about Dynamic NAT from this video, and I hope you found this useful. Stay tuned. Stay tuned. We'll be having another lab coming up very shortly today, on NetSIM. So we will. I will see you guys in that next video. So I hope you enjoyed this live stream, and I'll see you in the next video. Thank you for watching.